Let's get started with our second hour. Let me just say that for the portion we just ended up with on these, variations on SAT, the goal was to just give you a feel of it. We'll probably come back to this later. In fact, we'll probably do at least one reduction, so you will get to be more comfortable. This is just taking a peek at it at this point. I really want, we could have skipped that part. I wanted to make the connection to logical manipulations early enough so that you start visualizing things and seeing how important that can be. But if you are curious and can't wait, the tutorial on the YouTube channel which says on the role of logic in probabilistic reasoning and machine learning does this and takes it further. So it finishes the story on this one if you want to look ahead on the subject. Okay, so now we get to the second component of your chapter 5, which is dedicated to building models. And as I said in this particular chapter, the focus on two types of construction methods. One where we synthesize models from other type of information, and we're going to see example of that. And the other kind of the old traditional fashion where you really construct these things by hand. So what we're going to do next is walk through a number of examples. There are some of them little stories, and then we see what model correspond to that, and then what queries we're going to pause, and then they get successively more involved and more realistic. But each example has a story behind it. So each example that we're going to do, we will make modeling observations that apply actually more broadly. So the first step is in a building Bayesian network is, of course, defining the network variables. And the network variables themselves can be viewed as three categories. What we call query variables, the ones we're interested in computing the probability of. The evidence variables, the one we know we're going to measure their values. And intermediary variables are variables that are neither. I cannot measure their values. I'm not interested in computing probabilities over them. Then you ask yourself, so why do I have to have these? We're going to see examples of that. They typically mediate the relationship between query and evidence variables. And when we build networks, we'll have to think always about what are the evidence, what are the query, what are the intermediary. But the key thing to realize here is this distinction between these three types, that's a task specific. So you tell me I'm building a Bayesian network to do this, then that defines what is query, what's evidence, and what's intermediary. If you're going to do something else with it, those definitions may change. The second part is, of course, building the structure. And you will find that if you're doing this in an automated or semi-automated way, you need to think about causality for this to work. It's going to be as simple as looking at every variable and trying to determine what are the direct causes for that variable. And finally, there is the defining the numbers or the CPTs. And here you're going to find the range of things, from estimating them from data, even if you construct the structure in an automated way, to subjective beliefs, to, as you'll see in some cases, they can directly come from the problem statement. So we're going to see all of these variations. Okay, here's our first story. This is a story from medical diagnosis, but just to give you the structure of this part here. We're going to look at this, we're going to look at the network for it, and then we're going to look at a variation of that network, and then we're going to make a whole bunch of points in relation to the two different networks that we're going to come up with. So what we have here is a classical problem. The flu is an acute disease characterized by fever, body aches, and pains, and can be associated with chilling and sore throat. The cold is a bodily disorder popularly associated with chilling and can cause a sore throat. Tonsillitis is inflammation of the tonsils, which leads to a sore throat and can be associated with fever. So you have to pass through this paragraph. And now you have to think of the variables that we need to have. And as you can tell in this story, these variables are either symptoms, right, or conditions, diseases, the things that one have. Let me show you how this would look like. Well, first a count. Did anybody has a count of how many variables we're going to have? How many symptoms? 5 symptoms? How many conditions? 3, 2, 3. 3 conditions. You agree with the 5 symptoms? Ah, good. Let's see. What was the 5th symptom? Okay, here's what I have. The conditions cold, flu, and tonsillitis. And then I have chilling, body ache, sore throat, and fever. The point behind this example is look at the following. Look what's happening here. It's not an arbitrary network structure where we got here. It's something that's very popular, commonly used. You have 2 layers, right? There's the first layer, it's all conditions, and a second layer, all symptoms. And that's basically it. And moreover, edges go only from the first layer to the second layer. It's kind of a bipartite graph. And in fact, in situations like this, people even made one more special thing on how to do the CPTs for these things, to the point where this class of networks, some people developed algorithms just for it, right? Dedicated for this class of networks. And there are some well-known from the old days medical networks that have thousands of variables that look like this. But doesn't have to be medical diagnosis. People also use it to do diagnosis in general. In fact, I don't know how it looks now, but the early, remember we talked about the Google network refill? Looked like this. The second layer is what you see in the text. The upper layer is the clusters, what they call clusters or concepts that refer to subject matters and so on. All right? Okay, so this is one class. And now, here's the variation on this. Someone would say, wait a minute, I want to make this simpler. So instead of having cold, flu, and tonsillitis, look what I'm going to do. I'm going to lump these all in one variable. And I'm going to have this. I'm going to say condition. And then it has four or five, 3 values, 4 variables. So 3 plus none. And this, right? Okay. This guy is also quite common. And it's known as a naive Bayes structure, right? This is known as a naive Bayes structure. This is known as the class variable, and these are known as the attributes. It comes out a lot. By the way, this separation, can you tell me anything about this guy? What does this separation say? Are these 2 guys separated? Given that. In fact, given the condition, any 2 features are deseparated. That is independent. And that is actually the characteristic thing about the naive Bayes structure. Okay, let's look at some interesting distinctions between the 2. When put in the context of diagnosis, the difference between these 2 guys is also phrased as this. This assumes what we call the single fault assumption. The minute you lumped all of the guys in one variable, what did you assume? Only one can happen at a time, correct? This guy allows any combination. That's the best or simplest summary of the difference between the 2. Sometimes single fault assumption may be okay, sometimes it's not okay. But let's see some differences as well and help us also practice this separation. Suppose the patient is known to have cold, right? This guy. What happens in the naive Bayes structure? Fever and sore throat become independent, correct? These are we know that from the properties of the naive Bayes. Now, what happened here? Fever may increase our belief in tonsillitis, and that may increase our belief in sore throat. See, look at the structure here. There is no independence. All right? Okay, this is one distinction. Here's another distinction. Suppose the only evidence we have is that body ache, right? Body ache. Now, we expect the probability of flu to go up in both networks. Body ache, flu, body ache, flu. Now, what happens in the naive? This leads to dropping the probability of cold or tonsillitis, correct? You have to add up to 1, the 3 of them. One of them went up, the other 2 has to go down, correct? What happens here? Body ache. What is the relationship between this and cold? Are they deseparated? They are. You can prove here independence. These probabilities remain the same since both cold and tonsillitis are deseparated from body ache, right? You don't even have to look at numbers. by looking at these structures and being able to read the independence information that's entailed by these models, you can do quite a bit of reasoning about what's going on. There's actually more even differences between these guys, but let's move on. Oh, well, one more point about this and we go to another example. The one point which just planting the seeds here for our discussion later on learning. How do you quantify something like this? You quantify something like this, you can go to a doctor and say, can give me the numbers, the CPTs. Not a very pleasant task to try to get a doctor to give you these numbers. Sometimes these statistics have been collected, but the thing that we're going to talk about later is you can learn these from data. You can estimate these CPTs or parameters from data. So, but first, what is data? Again, just to prepare for the future, data looks like this. Here are the variables we have, and think of each row as a particular patient. And what this means, the question mark means I don't know that about this patient. So this is patient 1. They had a cold, didn't have a flu. I don't know whether they had tonsillitis. Yes, okay? And you have a lot of these. And of course, there could be duplicates because 2 different patients may have the same symptoms and diseases, or I may know something about them. So the idea is I give you data like this. I give you the structure, and I tell you estimate the parameters. And what does that mean? The common thing is to do what people call maximum likelihood parameters. That is, you choose the parameters that maximize the probability of seeing this data set. All right? So the way this works is if you look at each row as a variable instantiation, right? What you do is you generate a set of parameters that maximizes this quantity. Here we're iterating over all patients, 1 through n, and for each I'm computing the probability of seeing that patient and taking the product. So I'm assuming these are independent cases. And again, the idea is to learn parameters that optimize this quantity. We'll talk about this later. That's in your chapter 17 and 18 in the book. We will say a lot about this later. Okay, let's take another example. We've seen it actually already, and we're going to make a few points on this one, as you will see. So this is the artificial insemination procedure, and we have a scanning test that we are told has a false positive of 1%, false negative of 10%. And then we have the blood test, which detects progesterone level. And again, it has a false positive and a false negative. And then the third test is the urine test. Again, we're giving the false positive and negative. We're also told that the probability of detectable progesterone level is 90% given pregnancy and 1% no pregnancy. And finally, the probability that insemination will impregnate a cow is basically 87% in this case. So our task is to build the Bayesian network. You've seen it. Here's how it looks. The key thing here is, actually, what is the query variable in this case? Pregnancy, right? That's the one I'm interested in. What are the evidence variables? The test, the 3 tests. And then progesterone is intermediary. I'm not computing the probability of that, and then I can't measure it. And one of the things we're going to look at is, why do I even need it? Can I get rid of it? Right? We're going to say something about this. But just look at the CPTs. By the way, the CPTs are not full. We're only showing the numbers that are non-redundant. So for the 3 tests, you're going to see the false positive and negative rates, right? This is the false negative, and then false positive, and so on. For each one table, we're only showing enough, and you can fill in the rest. So here's one of the points we're going to make about this example, which also gives us a little bit of intuition and prepare us for the discussion towards the end of the course on sensitivity analysis. All right, so let's say we're using this network. I measure all 3 tests and look what they come out. Scanning negative, blood negative, and the urine is negative. All of them are negative. I plug them into the Bayesian network. I compute the posterior on pregnancy. What do I get? 10% basically and 90%. All right? Now, what was it before? It was 87%. So it dropped from 87. That's the prior success for this procedure. It went down to around 10% when all 3 negative tests came out negative. Now, we've seen this in the first week, where you may look at something like this and say, 10% it's good that it went down, but that's not conclusive enough. If I did all of my tests and they're all negative, that's ruling out only to 10%. No, I need something a little bit more decisive. So the question is, maybe you say, I want the probability to be no more than 5% if all tests came out negative, which means you have to get better tests, right? And this is where sensitivity analysis comes in. And you can basically say, you put some condition, no more than 5%, and then here's what you get. By the way, this also you can try it in SEMIAM. There is a sensitivity analysis engine there. You go to it and say, under this particular evidence, I want the probability of pregnancy to be less than or equal to 5%, right? And look what you get. Here's interesting things. And let me just say before that this is doing what we call single parameter sensitivity analysis. That is, what happens if I change only one parameter? Because you can change multiple parameters, right? You get 3 recommendations. And the first one says, if the false negative rate of the scanning test was about this instead of that, you will actually drop the probability of pregnancy to 5% or less. That alone will do it. But what is it saying? Buy a better scanning test. Now, these two are interesting. What is this? Now, the prior on insemination or on the procedure was this, correct? It's saying if it was that, that would also happen. But of course, that doesn't make sense, right? I don't want to replace my procedure by a worse one just to make this happen. That wouldn't be right. And the last one is also interesting. It says if the probability of a detectable progesterone level given pregnancy was this instead of that, also it's not under control. So these are not useful here. This is useful, right? I can buy a better scanning test, and it's telling me what test to buy. Now, there's something that is even more interesting than all of these 3 points. Where is the other tests? They're not here. What does that mean? This is saying, don't waste your money on the other tests. Even if you get perfect tests, it's not going to do it. Even if you buy, now, be careful here. We're talking about changing one test. Maybe changing multiple is another story. Changing one test. Now, why? Look at it. Because these tests tell me something about this, and this tells me something about that. This link here is weak enough in this case that these 2 guys, even if they confirm this, that will not propagate up there. Now, if you weaken the condition a little bit, let me see if I'm doing this right. If you go for 8% instead of 5%, they will actually pop up. They become relevant. And you get 2 recommendations in that particular case. So buying better tests can help you in dropping the probability below 8%, but not 5%. It's actually pretty interesting. You can do many other things with this, but let's move on. Okay, I just want to do one more thing before I go to the next example. You may say, let me go back to this network. You may say, why do I need this, right? So you may be tempted to say, let me get rid of it. But what does it mean to get rid of it? You remove it, and then you make this guy point directly to this, and make this guy point directly to that, right? And then you get a network over those guys. It says, look, all I'm doing is asserting evidence on these computing that. Let's get rid of this in a pre-processing step, and then I keep the smaller model. Okay, you got to be careful. Sometimes you can do this, and sometimes you can't. Now, what does it mean you can or cannot? You want to guarantee that if you do this, if you remove this guy, and this becomes the parent of that, this becomes the parent of this, you have to change the CPT on this guy, right? And change the CPT on this. Sometimes you can do that while making the 2 equivalent, meaning for your queries, they will give you the same answer. In that case, you're good. Sometimes that cannot be done. And we're going to see that the guy that you bypass, if it has a single child, you can always do this easily. But not in this case. It has multiple children. So you can look at the example in the book. But basically what's going on here is the example shows you what happens if you remove this guy and add these two links, that the two guys will end up not being equivalent. And in fact, it also uses deseparation to even predict that that's going to happen, because you're going to get a naive Bayes. Once more, look at the difference. This guy says these two are independent given pregnancy, correct? This is not true in the other guy. You already know that they're not going to be the same based only on the separation. It's fun, and you can see again in the book what happens when two tests, one model views them as independent, the other does not. What does that mean in terms of their evidential power? But we're going to move on. And this is the case where you can do that. This is X. It has a single child, Y. In this case, I can bypass this variable. I can remove it, make these guys parents of Y, as in here. And there is an equation that tells you how to update the CPT for Y in that case. And again, single child works. You will get equivalence between the original and the other one. We're going to actually use this technique later. This has been all doing what we call in the book models from expert, right? You're thinking about a problem, you're doing it manually. The next thing we're going to be our first automated example, where you will see how you can construct a network automatically from some kind of other information. So we're going to do it on digital circuits, but what we will do actually applies more generally. In fact, this technique, what you're going to see here, very practical. If you remember in the first hour in the introduction, I mentioned this NASA model that we built for reasoning about power systems. That would be this kind of technique. And the way it works is this. I give you a problem like here, circuit, right, with 3 gates. And the goal is, I wanted to do the Bayesian network about this to reason about the health. So later I tell you, here I applied this input. I got this output. Is this normal or not normal? If it's not normal, what should I blame? All right? And you can do similar things. The way we're going to do it now is we're going to reason about it and pick up the nodes, pick up the edges, think about the CPTs and so on. So usually with these things, you do this once. Once you do it, you look at it and say, oh, I see. Now I can automate this. Meaning, I figured it out to the point where I can write a program where you give me any kind of circuit, it will spit out the Bayesian network and do everything. No human intervention. So you actually do the exercise once, but then you figure it out for a whole class of systems. Now, even though we're going to work with circuits, whatever we're going to do applies basically to all kinds of systems that people can usually characterize using what they call function blocks. Systems where you have boxes that take input and generate output, and then you wire them in a certain way. Very general class of systems. So the selection of circuits as the concrete example is not to be misunderstood, that this is specific to circuits. Well, quickly, look at it up there. Anybody can tell me what kind of variables we need? I need to be able to speak about the state of each wire, correct? That's 5. What else? If I'm doing diagnosis, I need to be able to talk about the health of the gates. So I need basically a variable for each guy. Look how it's going to look. The evidence variables are the primary inputs and outputs, right? So I'm giving you, I'm telling you, I know what A and B is and what E, right? We need these guys. I'm asking you about the health of the gates. That's X, Y, Z, correct? And there are intermediary variables, C and D. I'm assuming here that I'm not gonna measure them, but I still basically need them. And here's how it's gonna look. Okay, let's stare at this for a little bit to see what the pattern, and then I'll explain what's going on. So this structure for the Bayesian network can actually be, you'll see now, it's something that you can generate automatically. But the general idea is this. And again, think of function blocks in general. This is the inverter, right? I have 3 variables relating to it. A, which is the input, C is the output, and X is the health mode. We call that the health mode, right? Now, the output is directly caused by 2 things, correct? The input and the health mode. And that's what you're seeing there. Correct? So this guy generated this fragment. Same thing for this gate. The output D is directly caused by A, B, and Y. You guys see what's going on? And similarly for the last guy, E, or this gate, the output E is directly caused by C, D, and Z. You basically just wire them up. It's pretty simple in this particular case. By the way, what are the values of A, B? These guys, A, B, C, D, E, these are on, off, right? What about X, Y, and Z? What are the values of these? You could do this, which is okay or faulty, but sometimes people talk about fault modes. That is, I want to specify in the way in which something failed. In this case, you can say stuck at 0. The gate will always generate a 0 regarding what you give it. Stuck at 1 for inverters, input, output short, and so on. Now, you're going to see the significance of this in just a second. But you're talking about, again, do you have fault modes or not? That's what people say in diagnosis. And let's look at now the CPTs. So the short story here is, with one exception, all of the numbers in this case can also be generated automatically. Why? Look, you have three classes of CPTs in this case. Those for the primary inputs, right? Because that's one category. And then you've got the gate outputs, C, D, E, and then you've got the component health, X, Y, Z, right? If I know how to do one of each, then I'm done. So let's look at them one by one. The CPTs for health variables is the information that you need about failure modes, right? So in this case, 99%, okay, it fails 1%. In this case, you have that. And this, we're going to assume that you're given. And in your book, actually, there is a section about these, where do people get these numbers from? There is, there is reliability engineering. It's a field. There are even, I'll maybe give you a hint later, things called life distributions and so on. So people know a lot about these things and how to estimate them for devices and so on. So we're going to assume we have these numbers. That's the only thing that you need as an input in addition to the circuit, which is these failure probabilities. And you're going to see that basically everything else can be automated. Look at the CPT for a component. Look what happens here. This is the inverter. The output is C. The input is A, and this is the health mode, right? These are all combinations. Look what's going on here. What is that? All zeros and 1. If the, when it's okay, when the inverter is okay, I know exactly the relationship between the input and the output, right? So it's going to be 0 and 1. If it's stuck at 0, stuck at 1, all of that I know. So this is what we call a deterministic CPT. Everything is 0, 1. There's no uncertainty. It's like a function, right? Completely automated. If I know how inverters work, and I know what is the meaning of stuck at 0, stuck at 1, done. Right? That is automated. Now, you didn't want this. You wanted healthy and not healthy. Look what happens. You do that. If it is okay, healthy, again I know what's going on, right? 0, 1. Correct? Now, when you have faulty, what do I put here? When you tell me that the inverter is faulty, and I tell you the input is high, the output is high, what do I put here? It's not clear. Correct? I don't know what is the failure mode. Anything can happen. What do you do in this case? Let's say you're faced with the situation. The class stopped here. You're not going to gain any more knowledge about these things. You're home, you have to solve this, and someone says, you've got to put some numbers there and get me an answer, otherwise you're fired or something. What are you going to put in there? The 2 numbers. Just make something. 0.5, 0.5, right? It's okay, good. That's what people did. You put 0.5, 0.5. Now, you have to be careful, because that, it sounds like I didn't see anything, or I'm being indifferent, but actually that is a very specific piece of information. You look at this, and we stop here again. I say, which one are you going to do? You going to do this or that? And you say, of course I'm going to do this, right? That looks easier. I didn't have to make any arbitrary choices. I did it here, correct? Not really. Look where it's going to come back to you. Any guess where this is going to come back? Look at the difference between the two. This case looks clean, right? I didn't have to make any arbitrary choices. And this, I had to make something arbitrary. When you did this, you said, okay, 99, not okay, 1. Now here you say, okay, 99, but now you have to tell me when it's not, if assuming it's only stuck at 0, stuck at 1, how is the 1% going to be split between these two? You have to enter the information here now. And in fact, when you put 5 half and half there, that's the same as splitting this also half and half. In the book, there is a more detailed analysis of this showing the equivalence and all of that. So it's really, in a sense, you can't escape. You need to enter this information one way or another. Let me just make one more observation here. Now you're going to tell me, okay, so the health modes, I'm getting these from failure estimates. For the gates, that's easy, 0, 1, deterministic. There's one more group left for CPTs to finish this off. The inputs, the primary inputs. Now this is a nasty one. What does that mean? That means what do I expect usage, right? What kind of input vectors? Now, how are we going to pull that one? Well, interestingly enough, it doesn't matter for the kind of queries we have. So, what is the query we have? The query is I'm going to come to you and I fix the variable, the inputs and the outputs and ask something. And that doesn't matter what you put on the inputs as long as there are no extreme probabilities 0 and 1. So if you put 0.5, you're good. In the sense, again, once more, it doesn't matter. And if you want to see why it doesn't matter, your book has a derivation showing that for this kind of query, where I'm trying to look at the posterior over H. H is the health variables. Given I and O, input, primary outputs, that's the query I'm interested in. It does do the simplification to eventually show that it's basically independent of the distribution you have on the input. All right, so it actually, and this is one of these nice things where you get the graphical modeling together with knowledge of low probabilities, and you can see base conditioning being used, chain rule, deseparation, all put nicely together to come up with a non-trivial observation about this model that I don't care about these numbers. They're not going to affect anything I'm going to do later. It's a beautiful combination of things. You can look at this derivation in your book. Let me actually do just a quick example here. Here's a test vector. Here's A, B input. Here's the output. And what we're doing here, we're going to do the map over the health variables, right? So this is the evidence, and I want the most likely instantiation of the health modes. And in this particular example, you get 2 of them actually. It says, so this is an unexpected input. When according to the circuit, if it's functioning correctly, when the input is high and the both are high, the output is also high. But I get this, and it says, okay, you've got one of 2 things. Either Y is stuck at 0 or Z is stuck at 0. That's what the 2 most likely health states according to this guy. And this was the example. The query I'm going to pose is the following, and then we'll look at it next time because that introduced the whole modeling technique. Here's the query. How many of you have done digital logic lab where you sat there and played with circuits and they didn't do the right thing and start missing? Okay. All right. One of the things you do is sometimes with this is, okay, you tried some input and you just didn't get the output. Either this or that, I don't know. You said I can probe wires, one of them. The other thing is, the other technique you do is what? Another technique in which you can isolate further beyond probing intermediate wires. Where's the debugging skills in you try another test vector. You say, let me see what happens if I change the input, right? You try another input and see what the output is, and maybe the 2 together tell you, oh no, it cannot be this or that, must be that, correct? This is what we want to do here. The question is, how do I do that? The way we set this up, you give me primary input, primary output. I assert them as evidence. I commute map over health modes. Now I want to give you 2 or 3 test vectors. And I want to say, give me the map or the most likely state of the health modes, assuming that when I applied this input, I got that output. When I applied this input, I got that output, and so on. How do you do that? Right? Now, let me just again say one more thing, and then we leave it here, and we'll pick up on this later. Sounds obvious. Your model has to have enough variables to be able to capture the evidence you have. If you do not have variables that correspond to the evidence you have, you're missing something. So this is the hint about what may need to happen here. But again, we will need to spend about 10-15 minutes on this, so we will do this next time. All right, guys, I'll see you on Tuesday.